thank you. Thanks everyone for joining. My PhD depends on benchmarking and pushing boundaries of event camera performance for space and sky observations. Now, event cameras are relatively new technology still that are really only well understood by a handful of experts throughout the world. They've been recently achieved some really remarkable achievements in space applications. However, due to this lack of understanding, we weren't able to see as dim objects as we would like to. So I'm going to show you today how we go from the previous state of the art of being able to look at the sky and detect about, in this case, for this patch of sky, about 32 objects, to applying some new novel principles and new understanding about the DVS pixel to achieve about a 3 times increase in the number of stars we're able to see with the same camera. So let's back up a little bit and talk about what are we looking at in the sky. So one of the big key issues we're facing right now is space since 1957 has started to become much more crowded with objects in orbit. To the point now we have over 10,000 artificial satellites in orbit, with an additional 1,400 or so projected through the year 2030 each year. So obviously, as we get more crowded, the probability of collisions becomes much more likely. And space domain awareness, or SDA, is the task of detecting, tracking, and deconflicting these satellite orbits to avoid collisions. So what's the benefit of event cameras for SDA? So we can compare conventional cameras on the top to how an event camera works. So a conventional camera is taking a sequence of snapshots or pictures, we call these frames, and stacking them together. We have a lot of redundant information, whereas an event camera only records when it sees a change in the scene. We can have much more data sparsity, and we can linear interpolate between the frames, so we get much higher temporal resolution. Now, all of these benefits include low data rates, low power consumption, higher temporal resolution, reduced motion blur, and a wide dynamic range. And these are all useful for space applications. So at the beginning of this research, I identified my main goal was to better predict the capabilities for space applications and also improve performance through a deeper understanding of the pixel architecture. So some of the obstacles that we faced at the beginning were we had kind of limited sensitivity. We weren't able to see as dim of objects as we hoped to. Part of this was due to noise in the pixel, and there were also inaccurate characterization methods, which led to incorrect predictions as to what the technology was capable of. I identified all of these obstacles come down to the root cause of what I believe to be an incomplete or flawed understanding of the fundamental design and operation of the pixel itself. And I identified 3 solutions based on a deeper understanding of the pixel. First is optimizing the biases or sensor settings, which we're able to tune through the user interface. Second is looking at the noise statistics to see how noise propagates throughout the pixel and if there's anything we can do to better manage the noise. And finally, we applied some realistic simulations to analyze the accuracy of characterization methods and figure out where we were going wrong before. So let's just quickly back up to the fundamental pixel. The DVS pixel takes photocurrent, compresses it logarithmically to an output voltage, which is then amplified around a reset level. This reset level corresponds to the last memorized brightness level of the pixel. And then the change from that last reference is compared to either an on or off threshold. If my signal increases, I get an on event, and if it decreases below the off threshold, I get an off event. After an event is generated, I wait a refractory period before the pixel is reset, the reference is reset, and I begin tracking changes again. Now, there's several degrees of freedom I have to tune the operation of the pixel or performance. First is the refractory period. I can adjust how much dead time there is between events. I can also change the bandwidth, so I can low pass filter the output of the photoreceptor. And thirdly, I can independently tune the on and off thresholds. There are also a couple of non-ideal behaviors that I need to be aware of when looking at the pixel. Obviously, there's noise, which leads to events that are unwanted. So events that are reported even when the signal doesn't change, only because of noise on the input. And then there's also mismatch. So mismatch actually occurs between different pixels, and it also is between the on and off thresholds in a single pixel. So let's just look at how a single pixel is going to respond to a changing signal. So if I have the output, the logarithmically compressed output, increasing then decreasing, I first track the changes until the output reaches the on threshold. I generate an on event, reset the reference level, and wait a refractory period before tracking the signal again. So for a signal that looks like this, I get three on events on the rising edge and 3 off events as the signal decays back down to its original level. So we also discussed how noise is important in the pixel, right? And before this study, we only really knew 2 methods to manage noise. It was either reducing sensitivity or reducing the bandwidth. So let's just consider this arbitrary DC signal with some noise. And over some time period, some time frame, the noise is going to push the signal above the on threshold or below the off threshold, and I generate these unwanted events that are not corresponding to any real signal change, but only noise in the circuit. So I can increase the thresholds, making it less likely to cross the on and off threshold and reducing my noise rates. Or I can low pass filter the output of the photoreceptor and also reduce my noise rates. But again, this is not an ideal approach because I'm trading off performance in terms of sensitivity or bandwidth. So the key discovery we made as we were studying these noise statistics is that event pairs, if I look at sequential event pairs in a single pixel, they tend, more than 90% of the time, we see opposite polarity pairs. So off then on or on then off, vice versa. Whereas only less than 90% of the time, or 70% of the time, we see same polarity pairs. So if we can understand why this happens, there may be some new things, new applications that we can use to manage our noise rates. So it turns out it's actually really, through a simple thought experiment, we can understand why this occurs. And it's really just a result of the pixel reset logic, which we said before. Remember, it memorizes the log intensity after each event. So let's consider the same signal. As it dips down below the off threshold, I'm going to generate that off event as I predict. But then I'm resetting my reference level, which is now offset near the bottom of my noise level, which makes it much more likely as the signal deviates back towards its mean that I'm going to generate a subsequent on event. Likewise, after this on event, I also reset my reference near the top, the opposite side of the noise level, making it much more likely that I'm going to generate this following off event. And this sequence continues and continues, which increases my noise rates unnecessarily. So what this reveals is there are a couple new biasing techniques that I can apply to be able to simultaneously increase my sensitivity and reduce my noise. And the one I'm going to discuss that was very impactful for this research was deliberately setting imbalance on off thresholds. So if you look over here to the right, my on threshold is just a little bit, is very, very low, but my off threshold is quite large. And what this does when I apply this method, we see that my reference level now starts to float to the top of the noise distribution, making it very, very likely or very, very unlikely that I'm ever going to generate this off event because the off threshold is so large. And when we actually apply this to the pixel, what I found was by applying a very imbalanced on and off threshold, I can reduce noise by 80% and achieve a factor of 2x increase in sensitivity to on events, which is very useful for space applications. What this also allowed us to do was we looked at this and we said, well, maybe we can actually do a more realistic simulation of noise simply by adding Gaussian white noise to an event generation model. So we did this and we were able to apply this new noise model to assess some various methods for and figures of merit for event camera characterization. So the one I'm going to discuss today is what do we think is the most important figure of merit for an event camera? I would argue it's the threshold. How much signal change is actually needed to generate an event? So we looked at what was there in literature before, and what's emerged as probably the most popular of the characterization methods for threshold is called the step response probability, or S-curve. It's a relatively simple method where we apply light pulses of very low contrast initially. We gradually increase the contrast threshold, and we observe the pixel response probability for each of these sequences of pulses. If the amplitude is below the contrast, we expect 0 response. And if the amplitude is above the contrast, we expect 100% response. We extract the 50% probability point, and we call this the nominal contrast threshold. This is what has been used predominantly over the last 5 or 6 years for characterizing event cameras. As we add noise, what we expect is this curve is going to shallow and pivot around this nominal contrast threshold. But when we look at what has been previously reported, so this was reported in 2020 for one of the latest event cameras on the market. And we see something a little bit maybe concerning here, is that the contrast threshold appears to change depending on the illumination levels. So we have 8 different illumination levels tested, both with on and off thresholds, and we see that this changes. So why should the threshold level change with illumination? Is this correct? So this is why we decided to study this method and see if there was anything we're missing in the theory. So we applied the step contrast, or the S-curve, to our pixel simulation. And with ideal conditions, if there's no noise, we get exactly what we predict. So I know my log contrast. I have exact ground truth of what that is because this is a simulation. And I see that I'm only limited by the resolution of measurement samples. But as soon as I apply noise, something different happens than what we would expect. What we see is that our nominal contrast threshold now shifts much further left than the actual contrast threshold. So I was expecting, I know my contrast threshold is 0.3, but my nominal contrast threshold predicts something less than 0.2, which is not really ideal if I'm trying to characterize the honest performance of my sensor. So what we see here now is we can relate this to actually a neuroscience principle known as stochastic resonance. And essentially what this means is that by adding noise to my signal, I'm actually only increasing the probability that I'm going to detect a small pulse. I'm never actually going to decrease the probability. So rather than using nominal contrast threshold, or NCT, I propose we use 90% probability intercept as an accurate method of extracting the true contrast threshold of the sensor. Now, if I go apply this reasoning back to this, what was reported before, I can look at these 4 brightest illumination levels. And what I find is this curve corresponds to a light level that's more noisy, and this curve corresponds to a light level that's less noisy, as predicted by simulation. However, now when I use my 99% intercept, I find that the response is more stable, and the true contrast threshold I can predict now is closer to 30% than what was reported, compared to what was reported before as something like ranging between 13 and 20%. I also, with our simulation, we can show that at these very dim light levels, the reason this curve starts to shift to the right is due to approaching the dark current limit and reduced bandwidth in the dark. Okay, so now we're going to move on to the last result, which is optimizing biases for space domain awareness and space applications. So what I did first was I conducted a lab experiment. I set up something to simulate very small moving point sources of varied brightness levels. Consists of an anodized aluminum disc with very, very small holes drilled in the front. I rotated it using a motor in front of an opening of a light integrating box, which I could control the brightness of the point sources. And then I recorded this with an event camera. So on the left side, you see what the output looks like when I record these streaks passing along. And this output, or this setup, is very nice for us because it allows us to test multiple different bias configurations with a consistent setup. What it also allows us to do is I can map the angular position of the motor to the XY address on the focal plane, which allows me to test perhaps a more noisy bias configuration than I would have otherwise been able to. And I can extract events that correlate, that of course correspond to when the target was actually on that pixel. So I could easily extract signal from noise in this sense. So when I apply this to something that's very, very dim, producing only about 2.7 thousand photons per second on the focal plane, I see, I can plot this out, and I see I have noise events in red and signal events. So signal events that are matched to the known position of the targets. I get less than 10% when I apply default biases. So these are the biases that have been typically used in every study prior to this. Now, when I apply some custom bias configurations, and turns out the best one includes a combination of imbalanced on and off thresholds, as we discussed before, a longer increased refractory period, and then minimized bandwidth biases. What I find is when I'm looking at the same brightness sources, I get greater than 80% response probability along these streaks. So that's a great result. I can also quantify how much more sensitive this is by now mapping the number of matched events I get per pixel for different point source brightness levels or on-chip photon flux. And what I see is for that same 2.7 kilophotons per second, I get 8 times the response for the same brightness. But then for the same response, say I map 1 event per pixel, so 100% response probability along the streak. And I see that for the same response probability, I get 2.6 dimmer objects with my custom biases than I was getting with the default biases. So that's great, but we also talked about how noise is potentially a problem here. And if I just look at the noise rates compared between the default biases and my custom biases, the picture doesn't look so great because I've increased my overall noise rates by a factor of 34 times. But if I look at the distribution, it tells a different story, right? I have this long tail of hot pixels that are dominating the noise rates. And in fact, if I dig a little further, I see that 93% of the noise events in this recording are caused by just 1% of the pixels. So if I can get rid of 1% of my pixels and I adjust my mean noise rate as a function of that, I realize that I've really only doubled my effective noise rate and achieved over a 2.5 times increase in my sensitivity. So let's look at this on sky. Let's see what we can achieve now with on sky results. So we went down to Mikhail Zanowski's observatory down in Italy, pointed at the sky, scanned across for 45 seconds, made some recordings. So here's what we got with the default biases. As I showed you in that first slide, we get 32 visible streaks after accumulating for 45 seconds caused by stars. And I have a very sparse 536 events. So a megapixel array, 45 seconds, and I'm only getting 500,000 events. So very sparse, 32 streaks. It's not so bad. When I apply my new custom biases, I'm able to pick out an additional 22 streaks, which is a nice result. But I've increased my noise rate by almost a factor of 200, which was predicted by the noise analysis before. So if I remove those hot pixels, in this case, I decided to move 2% of the hot pixels, I get down to 900,000 events, which is not even doubling the total throughput from before. And I now have 58 visible streaks. But there's one more thing I wanted to look at after observing how I could just remove hot pixels. So all known denoising algorithms are really looking for clues about a signal. For instance, we expect a signal to have some spatiotemporal correlation. But this may not always be true for the dimmest streaks we're looking at. There may be a very dim satellite or star that's only generating an event every 3 or 4 pixels. So spatiotemporal correlation is not necessarily going to get us what we need in that case. So I started thinking about what do we know about noise? And one thing that we know after all this noise statistics we studied is that noise tends to be fairly constant for each pixel. So if I look at a very simple method and I just assume that each pixel has a relatively constant rate over the course of recording, I can take a dark recording with no signal in it. I can calculate the average noise rate per pixel, and I can multiply that by the duration of my signal recording. And if I build a frame from that and subtract it from my signal recording, I can go from 58 visible streaks to 92 visible streaks. I'll just go back and forth a couple times just so we can have a little bit of comparison here. So what we found here is quite a remarkable result, which I think is really should be a focus of future research is developing more sophisticated denoising algorithms, focusing more on what we know about noise than what we expect about the signal. So in conclusion, I proposed 3 solutions to address some of the shortcomings I found in space domain awareness and event cameras, including bias optimization, noise statistics, and then applying realistic simulations. So through bias optimization, we achieved a 2.6 times improved sensitivity for space detection. Looking at noise statistics and then applying realistic simulations, we were able to correct a flaw in threshold measurement interpretation that gives us a much more accurate expectation of what the pixel should be able to accomplish. And then finally, when we looked at on-sky data with bias optimization and a very simple method of denoising, we were able to demonstrate almost a 3 times increase in the number of visible streaks. Finally, I'd just like to acknowledge, obviously, Toby and Shichi for their guidance throughout. Also on my committee, Giacomo, throughout the 3 years I was here, with everyone provided invaluable guidance in helping me along in my studies. Also my examiners, Andre and Vinny, thank you for taking the time to read my thesis and hopefully have some good questions. And then obviously everybody within the sensors group, Institute of Neuroinformatics, many of my collaborators throughout the Air Force and Space Force, Mikhail Zonowski at Six Roads, and then my most important, probably key collaborator who couldn't be here today, Rui, through hours and hours of conversations, he really helped me accelerate my understanding of the pixel and contributed to a lot of this work. Thank you.